quantile models can miss their promised coverage. Conformalized quantile regression uses MAPIE to adjust the intervals so uncertainty becomes more reliable. This is the workflow you'll know how to run when we're done, which calibrates quantile bands on history and applies conformal adjustments to new forecasts. I'm Professor Pi, teaching AI foundations with simple Python. Conformalized quantile regression starts from a practical worry. Your quantile model predicts lower and upper bounds, and you expect, say, 80% of outcomes to sit inside. But real data rarely behaves nicely. Noise can grow with the input, and raw quantile bands can undercover in some regions and overcover in others. That matters when you need dependable risk bounds for forecasts or automated decisions. The fix is simple to describe. Train your quantile learner as usual. Hold out a calibration set. Then use conformalization to learn a correction from the residuals. MAPIE is a tool that automates that step. It watches where the bands missed on the calibration fold and inflates or shifts them so the target coverage is hit without making distributional assumptions. Picture a toy time series where volatility rises with the feature. A straight quantile model will undercover the noisy tail. Conformalized quantile regression learns that correction from history, so new predictions come with more honest uncertainty, strength, finite sample guarantees under mild exchangeability. Weakness: it needs a calibration set that looks like the future. We'll build a compact, reproducible example with rising noise, fit plain quantile regressors, then wrap them with MAPIE and compare coverage. The code is intentionally minimal, so the idea is clear without production details. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we create the toy heteroscedastic dataset and split it into training, calibration, and test folds. This snippet builds a heteroscedastic toy dataset and shows how noise increases with the feature. The RNG seed keeps everything reproducible. X_all is a set of evenly spaced inputs. Noise scales with the feature to mimic rising variance, and Y_all mixes that noise with a simple trend. The call to MAPIE's train conformalized test split gives us train, conformal, and test folds to reuse. And the printed ratio compares the upper half to lower half noise spread, so you can see how strong the heteroscedasticity is before we fit anything. Now we fit a plain quantile baseline on the same splits to see how raw quantile bands perform. This example fits Scikit-learn's QuantileRegressor on the training fold and measures how the raw bands behave on the test set. First, we fit the lower quantile with quantile equals 0.1, then the upper quantile with quantile equals 0.9, so the pair directly forecasts an interval on X test. The Boolean check inside np.mean counts how often Y test falls between those bounds, revealing the empirical coverage. The printed coverage value shows how easily uncalibrated quantile regression can miss the nominal target when noise depends on the feature. We saw the naive bands miss their target in the noisy tail. Next, we hand that same quantile learner to MAPIE so it can learn a conformal correction from the calibration fold. This code wraps the quantile learner in MAPIE's Conformalized Quantile Regressor and targets an 80% coverage. Passing QuantileRegressor as the base estimator and confidence level equals 0.8 tells MAPIE the coverage goal. The fit call trains on xtrain while MAPIE uses xcal to measure residuals and learn the adjustment. Calling predict interval on xtest returns the recalibrated bands in intervals. The printed coverage shows how closely the conformalized intervals hit the promised reliability. The conformal correction can be asymmetric by default. But sometimes you want a single shared adjustment to keep the band symmetric. Let's compare both choices and see how the width changes. This snippet contrasts MAPIE's symmetric correction option with the asymmetric default. Base width records the mean span of the earlier asymmetric intervals as a benchmark. Calling CQR predict interval with symmetric correction equals true forces one residual adjustment for both bounds, producing sim intervals. We use np.mean to measure how much those symmetric bounds expand, and regression coverage score to check coverage. The printed width and coverage make it easy to see how enforcing symmetry typically widens the band while still aiming to preserve the nominal coverage. Finally, we check local reliability. A single global coverage number can hide regional failures, so we slice the test set by the input feature and inspect each slice. This code checks calibrated intervals for local reliability across feature regions. Mask low selects the calmer portion of X-test. Mask high picks out the noisier tail from the toy generator. And regression coverage score reports coverage for each slice. We also compute mean interval widths with np.mean to see how bands stretch where uncertainty rises. The printed metrics show whether both regions keep coverage near the goal while widening more in the volatile area. In a real system, you'd map the calm slice to typical operating regimes and the noisy slice to edge cases. Then decide whether you need more calibration data or richer features for consistent coverage. Recap: MAPIE's Conformalized Quantile Regression takes your base quantile fits and adjusts them using held-out residuals, so predicted bands meet a target coverage. Use it when you want more honest uncertainty estimates and can reserve a calibration split. Remember the catch: the guarantee depends on the calibration set reflecting future data, so distribution shift can break the result. Next step: tune the calibration size. Try larger or smaller calibration folds to observe the trade-off between estimator variance and correction accuracy. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.